Hello everyone, my name is Nikhil Kant and this is my Georgia Tech Physics 2112 Lab 4. So for the introduction, for the purpose of this lab, it's to predict the behavior of circuits containing resistors in series and parallel. And we also have to use multimeters to measure the actual values of conventional current and potential difference in the circuits, and also to examine the behavior of ohmic resistors and capacitors. So for our principles, we're using Kirchhoff's junction rule, which says that the sum of the current going in equals the sum going out, and also Kirchhoff's loop rule, which means the sum of the potential difference is zero for a closed loop, and also Ohm's law, which means voltage is equal to current times resistance. So for our first lab, we have a series circuit, which looks like this. We have two batteries, which both of them equal 1.5 volts each, 1 ammeter, two resistors, one being 47 ohms, one being 100 ohms, and then another ammeter. So for the series circuits, as you can see, we tested the volts at each point going down for the potential difference. And as you can see on the graph on the right, I measured the values, and the blue lines are the new ones I put in. And as you can see in the gaps between, for example, D and E and F, G, and GH, the total change is zero, and that's because the wires are ideal, so they have zero resistance. However, the two resistors have resistance, so therefore the amount goes down from each one. And between C and D, you get a negative 0.959 volts, and between E and F, you get a negative 2.041. And for the resistors, you can see the resistance of the 47 ohms is 47 ohms. And for the R wire and R ammeter, the resistance is 0 ohm. Also for the series circuit, if you're connecting the voltmeter across the 100 ohm resistor, the ammeter reading stays the same because the voltmeter has a high internal resistance. However, if you place the voltmeter with an ammeter in parallel with the 100 ohm resistor, then it alters the current because of the low internal resistance. For the RC circuits, for the circuit containing a resistor, bulb, capacitor, and battery, and that's what an RC circuit is. And then it is when the battery is connected, the bulb turns on, but however it fades over time while the capacitor charges. However, when the battery disconnects, the bulb turns on and fades with time while the capacitor discharges. And from this, we know that the current is associated with light behavior. For charging and discharging the capacitor. So, for the time a capacitor to charge and discharge varies with the resistance. For example, with 10 ohms, it took about 9.7 seconds to charge. And for 20 ohms, it would take about 19.2 seconds to charge and discharge. And as the resistance doubles, the time doubles, and this means that it is directly proportional. And then, so I plotted all the times down, and I took some graphs, and as you can see in the top right, voltage versus time, the line is linear between the voltage and time. And in the bottom graph, if we take the natural log of V over V naught, and then versus time, we do see that the graph is linear, which is what we would expect. And the slope is negative 0.169. And to find the RC, you take negative 1, divide that by the slope, and from there I got 5.917. Now, in an ideal conditions, you would have the RC equal 30 ohms times 0.2, which equals 6. And as you can see, 5.917 and 6 are very close in value, which makes our experiment true. So for the what ifs. What if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter, and how would it affect the circuits you've hooked up to? Well, a real ammeter has an internal resistance, unlike the ideal ammeter, which has an internal resistance of 0. Everything in real life, even though we try to make it ideal as we can, will always have an internal resistance. And because of this, there would be a drop in potential difference and a reduction in current. Now for the second what if question. what if you're doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict their capacitor to reach full charge? How would this prediction happen in real life? Well, our ideal model would have the capacitor being charged instantly. However, in real life, there would be some resistance, so it would not be instant. It would be very close to being instant, however, it would not be instant. That is it. Thank you.